So Jim's going to have a great talk. He's a great speaker. He's very very knowledgeable and quite an expert in reservoir engineering, and so I think we'll enjoy the talk this morning. I just wanted to tell you a little bit about him. He graduated from Penn State in petroleum with a PhD in petroleum engineering in '74. I thought it was '76, and he was giving me a hard time for making him sound younger than he is. But worked with production analysts, which was the precursor to OFM. Back in the day, and he's worked at JS Nolan, OGCI, IBM E&P, and he's been with CMG for the last 17 years. The past 6 with CMG as VP US and Latin America, and especially over the past couple of years, a lot of exposure to our unconventional modeling and those customers in North America. Jim.
Thanks a lot, Ryan. And thank you all for taking time out of your, I'm sure, hectic, busy schedules to come and listen to a kid from Erie, Pennsylvania that has been in the oil industry since '74. A couple weeks ago, I had the honor of chairing an SPE forum series on numerical modeling of unconventional reservoirs. We were dealing with modeling of hydraulic fracturing, fluid flow in fractured wells, and geomechanics. And we had a nice little system set up called an audience response system, little clickers, where we asked questions of the audience. How many of you are using reservoir simulation? How many of you are designing fracs with software, et cetera? And the interesting one, we did it at the beginning of the week and at the end of the week. Forums are 5 days. And by the end of the week, the audience response to the question, how many of you think you should be applying numerical simulation to analyzing and optimizing your unconventional reservoirs, the percentage was 80%. Incredible, okay? And so I don't think there's any question, although I'm sure we could all argue the fine points, that people believe that reservoir simulation is a useful tool to help with working with unconventional wells. The question is making it work efficiently and in a routine enough fashion to where you can really use it on a regular basis. And that's what this talk is all about, how to use the tool in an efficient fashion with the capabilities that exist in the current release of the software. And I hope you'll see by the end of this presentation that, wow, this is something we could be using. A lot of you are using the tools, no doubt. But I want to make sure you can see what the full capabilities are to use CMOST to drive these models. And that's what we're going to try to do. So this talk, unlike many that I've heard on unconventional modeling, is about what we can do today, okay? I'm going to lay out the workflows. This is how we do it at CMG. This is how you could be doing it as well. Maybe you already are. I hope so. But and then at the end of the talk, we'll talk a little bit about futures. Some of the other things we're working on to try to enhance the products to make them more usable for the rest of the groups. So let's go ahead and get started. First thing we're going to do is review a little bit of the physics that are captured in the reservoir simulators that we use for unconventional wells. And then we're going to apply that physics to answering the 3 big questions that I find that people want to know about when they're analyzing or looking at their unconventional wells. How to calculate EURs from limited data. This is not the minimum B-value approach, right? This is trying to use numerical modeling to get physics-based answers, okay? And then with that information, how to optimize well completion designs and, of course, well spacing. How many wells should I stuff into that one section, okay? So we're going to try to show the workflow. We're going to show the workflow for doing that. A lot of the stuff I'm going to be talking about, you might suspect I'm very biased by our approach and our technology, but we're going to show you some recent SPE papers that talk about analyzing these wells using our technology, and they're from a wide variety of companies. And then lastly, we'll give you a quick look at the number of companies that have licensed our technology for analyzing unconventional reservoirs. And that's a pretty extensive list now. when I started giving these talks in serious mode about two and a half years ago, I think we had about 8 companies lined up on the list that were applying this technology for unconventionals in the U.S. There's now over 38 companies between Canada and the U.S. Now, that's E&P operators. I'm not counting the consultants or the service companies. So it's quite a big list. So it's giving us a lot of feedback on how to improve the process as well. So let's go ahead and get started. I think most of you know that this is our particular suite of products at CMG. The ones we focus in on for modeling unconventionals are the black oil simulator IMEX and our compositional simulator GEM, and we'll talk a little bit about when to apply which one in just a minute. We're going to talk about building models with Builder and how easy it is to create the proper gridding required to model transient flow from matrix to fracture in these models. And then we're going to talk about the thing that makes this all really happen in an efficient way, and that's CMOST, I call it our productivity enhancement tool for doing automatic history matching, optimization, etc. We're going to see how CMOST works with Builder to help generate models automatically so that you can look at a range of parameters when you're trying to do history matching or optimization. It really, really makes it all work. So let's take a look at the physics. This is trying to summarize on one slide a lot of pretty important facts. Let's start with PVT data. In IMEX is a black oil simulator, but IMEX can also model primary production of volatile oils, gas condensates, and wet gases. So you don't necessarily have to go to a full EOS unless you're near critical or if you're trying to model some sort of EOR process with shale liquids like gas injection, CO2. I mean, people are doing that now in the States. I'm sure probably people are trying it up here as well. And the nice thing about IMEX, it's super fast. So as I said, there are occasions when we need to use the EOS approach to modeling these physics, but in a lot of cases for initial history matching of primary production and forecasting, the black oil approach is just as good. Adsorbed components. Back in the days when we switched over from coal bed methane to shale gas, I mean, this is sort of how this all evolved. You needed to be able to model multiple gas components that were adsorbed, as well as the free gas. So impurities like H2S, CO2, etc. In GEM, you have the full capability to have multiple components, each with their own adsorption, either Langmuir data or even tabular data. But even in IMEX now, the gas phase can be adsorbed as well. So even if you're looking at, say, a primarily pure methane type play where you have free gas and adsorbed gas, unlike the old days, you don't have to go to GEM to model that. You can do that right in IMEX, and it's quicker, to be honest with you. Some of the more sophisticated physics that are part of GEM come into play, like multi-component diffusion, and diffusion in all 3 phases in the model. When we start looking at EOR in shale liquids, and you're looking at injecting gas into these fracture networks and trying to get that gas into the matrix, diffusion is almost competitive with Darcy flow in some of these cases, depending on the level of matrix perm. So that capability exists in GEM if you're trying to look at that type of process. Let's talk about how we build the models. We basically create what some people might call a 4-porosity system, but let's not be so complicated with that. We always want to model natural fractures in these shale and tight reservoirs, even if they're sealed up originally. Okay? So we always use a dual perm approach, at least at CMG, because we need to have communication between matrix and matrix as well as matrix and fractures. Okay? And you'll see why in just a minute. The prop fracs, we're going to model those as corridors in the matrix, okay, the main prop fracs, using our logarithmically spaced, locally refined grids, and that's 2/3 of what we refer to as our tartan gridding system, LS, LR, DK for dual perm, okay? And we model those prop fracs explicitly in the matrix, okay? So we have fluid flow from the matrix through and from the natural fractures coming into these main prop fracs, which are corridors in the matrix. Okay? We can have more than just Darcy flow going on here. In the early days of shale gas wells, we found that we needed to model turbulent flow in some cases. As the fluid flow gets closer and closer to the wellbore, the velocities increase, and you can have a situation where you have additional pressure drop due to turbulent flow. And you need to take that into account when you're analyzing production data. Otherwise, you come up with these ridiculously low fracture half lengths if you don't account for that fact in your decline analysis or whatever you're doing. We even have slip flow. There's a lot of talk about slip flow in these environments. We'll get into that a little bit later. But we do have that option in GEM to model a Klinkenberg type effect. And that sometimes can come into play. Even when you put a well on production in the first few days, with fine gritting around those prop fracs, you can actually have pressures dropping low enough to where things come out of solution, but you can also have slip flow in some cases. Rel perm and cap pressure. Every reservoir simulator can have different rock regions, right, where you have different rel perm and cap pressures. Usually we associate that with different rock lithologies in the matrix, but here we're really referring to the fact that we're going to have different rel perm curves in the matrix, in the natural fractures, and in the prop fractures. And these things need to be able to change with time. They need to be able to change with time, especially if we're going to model refracts and we're going to model wells coming on production at different times. We don't want to put in all of the gridding and the frac information about all the wells from day one. It's very inefficient and it's actually not correct. So we've set this whole system up so that everything that needs to change with time, including absolute perm when we add a new frac or add a new well, where there used to be just matrix perm, that's all doable with this technology. Okay? And then, of course, the big cat on the block here, pressure or compaction. We all know that these prop fracs decline in conductivity over time due to embedment, crushing, etc. And we've really got two ways to represent that in our software. We have pressure-dependent compaction tables. This is the cheap and easy way to do it, where you reduce permeability and even porosity in the prop fracs and the natural fracs as a function of pressure change. But we are seeing some folks take a look at our coupled geomechanics module, which is coupled to GEM now. I don't know if you know that, where we can actually try to model the change in permeability of these prop fracs as a function of stress change. And we even have in this geomechanics module a constitutive model that deals with creep, where it's time-dependent change in perm at the same stress level. So there's lots of interesting things that you can start getting into if you're really getting into a mechanistic study of this process. We even have geochemistry in here. One of the talks at that forum that I mentioned was about how proppants, even ceramic proppants, are being degraded by exposure to brine and formation in injected fluid compositions, to where the mechanical properties of the proppant are actually being weakened as a function of being exposed to this stuff. Some of that stuff could actually be modeled in GEM with our coupled geochemistry feature as well. But that's getting really deep. Let's back up from that. And let's talk about the routine application of this technology. This slide, I know it's very hard to read this slide, but it does point out a few things here. That first of all, people have been using our software to model hydraulically fractured unconventional wells for quite some time. In fact, if you really take this back even further, back in the late 90s, a company called Fracture Technologies, a guy named Sammy Hadar, decided to use IMEX as the engine underneath his frac production simulator called WellWiz. Okay? I don't know if you've ever heard of WellWiz, but WellWiz was used in the North Sea to help model the hydraulically fractured horizontal wells there many, many years ago. And back in the middle of the 2000s, we decided we needed to incorporate the gridding technology into Builder to help generate those grids because we could see where the market was going with this stuff. So in 2008, we have our first version of Builder that has what we call the hydraulic fracture wizard. It could create the logarithmically spaced gridding to represent flow into a single vertical frac in a vertical well. So that was day one, okay? A year later, we expanded that to putting multiple single plane fracs along a horizontal well, all buildable with this wizard called the hydraulic frac wizard. In 2010, our Barry Rubin published his now pretty iconic paper on justifying the use of our logarithmically spaced, locally refined dual perm gridding technology, creatable in the hydraulic fracture wizard, showing how we could match analytical solutions for simple cases, for infinite and finite conductivity wells, and giving us the confidence to know that we could expand that to much more complicated cases. And also proving to ourselves, and hopefully the rest of the industry, that these fracture corridors don't need to be modeled all the way down to actual prop frac width. You can do it, but if you do, the run times are going to be days for one well, okay? We normally create these grids that have a 2-foot wide swath that represents the prop fracs. We alter the permeability so the conductivity is the same. We also alter the non-Darcy flow coefficients so that the simulator thinks that the velocity of the fluid flowing through that 2-foot wide swath is equal to the velocity that it would actually have at the actual prop frac width. So makes models that would normally be millions of cells, take days to run, get the exact same result with models that have much fewer grid blocks and take minutes to run. And you're going to see that term minutes to run come into play here as we go through the actual application. So, and the other thing here, as you can see on the screen, we can represent planar type fractures or complex fractures, which for us are intersecting planar fractures. And in the case of the complex fracturing, many of you know that we can import microseismic data into Builder to help delineate which grid blocks you think initially should be considered as part of the so-called magical SRV, simulated reservoir volume. You don't have to have microseismic to do this, but if you want to get a non-uniform type one, then you need to have some blueprint for microseismic to help do that. So that's in there. But going down through the rest of these spots, the big deal now that makes all of this usable in an efficient way is the fact that starting with the 2012 mid-year release of our software, and that came out February 2013, CMOST can tell Builder to build a new model that has a different gridding to represent different fracture properties. Before, you had to build all these models yourself ahead of time and then give them to CMOST and say, pick and choose from one of these. You don't have to do that anymore. You build one base model based on what you think you created with your frac job, and then you tell CMOST, I think the frac half length could be from X to Y, and the frac width could be Y to Z, whatever. And every time CMOST's experimental design engine says, create a new case for me, I want to test this combination of data, that fires off and runs Builder silently, and Builder creates a new model with that new gridding to represent that scenario. That is huge, because now the user doesn't have to interact with that process at all. And you'll see what that means here in terms of actually doing some work. So, prop frac gridding is easy. Now, I realize we're still using idealized representations here. But to me, knowing whether you basically think you're going to have planar geometry or complex geometry, it's a good starting point. In fact, when you analyze data or do optimization, you could start with the assumption that it may be either case. There's nothing that would keep you from doing that. So Builder creates the necessary gridding to properly represent transient flow from matrix to these prop fractures in either one of these geometry cases. That's important. And as I just mentioned, CMOST can tell Builder to create new cases without user intervention. Okay? So what are we talking about here? The things that you really don't know about, or maybe just have a best guess from a frac design simulation. frac half length, the propped frac half length after the job has finished pumping and all the proppant has settled where it's going to go, okay, which has nothing to do with microseismic data, right? That's the size of the fracs at the last time you're pumping, okay? The fracture permeability, how many pounds per square foot of frac surface area did you actually get put and where? The effective spacing, how many stages, how many perf clusters actually see a fracture created? We don't really know. It could be greater than the number of perf clusters. It could be a lot less. In fact, most of us suspect it's a lot less. Why don't we let the production data tell us that? And that's what you're going to see here in just a minute. And of course, if you're working with complex geometries, we can filter on the microseismic data. You know, how many microseismic events should we actually see before we count a gridlock as being part of the stimulated reservoir volume? Or what moment magnitude do I want to use as a cutoff? You know, it's kind of like a porosity cutoff. All of that can come into play inside a builder for delineating the size and shape of that SRV. So it's pretty powerful. It really gives you something useful to do with microseismic. So that's our overview of the capabilities of the software. Now let's apply it to answering three questions. How can I determine an EUR with limited data? Given that information, how can I optimize the completion design of a single well? And number three, how can I optimize the number of and the completion design of multiple wells in the same area of the field? So we're going to try to address all three of these with this talk. So physics-based EUR calculation, that's workflow number one. Pick the simulator that has the physics that you think you need to model your process. Many cases today that starts with IMEX. And it's a lot faster, so it's not a bad choice. Build a base case model that represents your best initial guess as to what you think you created with that frac job. Okay? And then use CMOST to perform sensitivity analysis. Which parameters are my cum production values most sensitive to? So that you can then focus on those for doing history matching. Once we get a history match, and we're going to get multiple combinations of data that give relatively the same level of history match error, not one. I mean, you can use one, but we prefer to use multiple, so that when we get a forecast of the EUR out 20 years, 30 years, 40 years, whatever you want to do, whatever criteria you use for forecasting, you're going to get a range of values for the oil EUR and for the gas EUR, which I think makes really good sense. So that's the first workflow. Key factor here, the engineer only builds the base case model, decides which parameters to allow CMOST to vary, and CMOST does the rest of the work. It fires off all the runs, it analyzes the data, it creates the next set of experimental data points, combinations of data, and you're just watching the global history match error change with time. Okay? So this workflow is going to be applied. This is a real world well. It's a 4,000-foot Eagleford lateral in the oil window. That number is incorrect. It's a 10-stage frac job with 4 perf clusters per stage. So it's basically 40 perf clusters. Okay? And I've got 7 months of production data, 222 days, and I've got oil and gas water rates daily. And in this particular case, I'm very fortunate. I've got measured flowing bottom hole pressure at the heel of the well. And I like to say one thing at this point. I don't care whether you're using simulation or decline curve analysis or whatever. Rates without pressures, absolutely useless. Okay? If you're trying to understand why your wells are producing what they're producing. Okay? Even if you're trying to compare well A with well B, if they're operated at different wellhead pressures or different fluid levels, different pump strokes, of course they're going to give you different rates. Could be from the exact same completion. So this statistical comparison without including things like the pressures at which you're operating or how you're operating your wells is just a lot of garbage, really, as far as I'm concerned. So the task here is to determine the oil and gas EURs, and we're going to do this by matching 7 months of history and then taking the best X matches and forecasting them out for 30 years of future production. So here's a couple of slides that really kind of introduce us to minimum levels of data that we need to do this process. I'm going to do this as simple as possible. Just because I have a reservoir simulator that would let me vary porosity and perm by grid block doesn't mean, number one, I have that data before I need to analyze this well. Doesn't mean you have to work with that. How about if we come up with the permeability and porosity on average that describes how the well behaves as a starting point? Then you can get much more sophisticated as your geologic modeling progresses to a point where you can import it into the process. So here we're looking at a typical deep, very high pressured, initial reservoir pressure 8,100 pounds at 10,800 feet. It's about 150 feet thick. It's hot, 270. Highly undersaturated, 3,000 psi bubble point pressure at an initial pressure of 8,100 pounds. It's going to be a long time before I have multi-phase flow in the matrix on this well. In a way, it makes life easier for us. Who cares what the rel perm curves are in the matrix? If I have single-phase flow, the water's mostly immobile in the matrix. I think we would all agree with that. It's going to be a long time before gas comes out of solution in the matrix. A lot of people talk about, why does the GOR stay so constant on these wells when my flowing bottom hole pressure is below the bubble point? Well, guess what? Inside that prop fracture, there isn't any critical gas saturation. It's straight line rel perm as you get equal flow. So you can have a long period of constant GOR before you drop the pressure in the matrix sufficiently to create multi-phase flow there. Now we're going to start getting into the less certain category of parameters, but these are the things that a reservoir simulator needs, okay? And even if it's a constant value per layer or for the whole reservoir, it has to have something along these lines. So matrix porosity, matrix perm, I really don't know what they are, so I'm going to give them a range of values. In this case, I'm going to let the effective matrix porosity, that's the effective connected matrix porosity, range from 4 to 10%. And my matrix perm, I'm going to allow it to range the whole gauntlet, 10 to 1,000 nanodarcies. If you know it's narrower than that, you can do it. But in this case, that's the range we're using. Now, in this case, I'm going to use my natural fractures that are stimulated next to the main prop fracs, and I'm going to give them constant values. In this case, I don't have to, but I just chose to do that in this case. So my effective natural fracture porosity is 6%. It's 0.0006, which is 0.06%. Remember, reservoir simulators want natural fracture porosity and perm, not the intrinsic values, but the effective values spread over the whole grid block. Okay? And so the natural fracture effective perm, I'm picking 40 nanodarcies. And my spacing, whether it's from some sort of DFN analysis or FMI or whatever, I'm just going to pick 50 feet, okay, as a starting point. The rest of these parameters, again, I think we all agree, the frac design software may tell us something, but we don't really know what the effective spacing is between planar fracs. We're going to let the simulator tell us that. We're going to let the production data tell us that. So I'm going to allow it to vary from the initial design of 100 feet. Remember, 4,000 feet, 40 perf clusters, 100 feet per cluster. But I'm going to assume that maybe not all of those got opened up. Let's see what the simulated data says, the history data says. Prop frac half length, similarly 50 to 400 feet. Some people say, well, it might be 1,000 feet. We'll make it 1,000 feet. Let the data tell you what it is. Prop frac perm, 1 to 30 darcies. And this is something pretty important. At CMG anyway, we always try to model and history match the flow back of injected frac fluid. Okay? Because it gives us some control over how much volume we have in the open natural fracs and prop fracs at the end of the job. Now we all know we don't get a lot of the frac water back or a certain percentage of it. I don't think much of that's leaking off to the formation. These things are really tight, depending on the perm level, of course. So I think what happens is a lot of these non-prop natural fractures, they open up during the pumping process, but then they close off at points, trapping some of that frac water. But we want to model that and history match it so that we have some idea of what that volume is. So we're going to allow a range of saturations in the prop fracs and in the natural fracs that range from 15 to 45% to help history match that part of the process. More data. Rel perm, my rock fluid data, my compaction assumptions. I mentioned this is a highly undersaturated reservoir. I put in a set of Corey functions for the matrix, but they're really not going to come into play in terms of history matching the 7 months of production here. In the natural fracs and in the prop fracs, I think most people would agree that representing those with straight line rel perms, probably with 0 and 1 endpoints, is fine. Okay? You don't have to assume that, but that's a pretty good assumption. Matrix capillary pressure, probably don't need to worry about it. I said I don't have multi-phase flow for quite some time, so I'm not going to worry about what it is. And of course, in prop fracs and open conduits, it's 0. Okay? There's no capillary interface. Here's what things get more interesting. Matrix pore volume compaction, natural fracture pore volume compaction. The one I'm really concerned about here is my compaction, my decline in prop frac permeability as a function of changing flowing bottom hole pressure in the well, which gets transmitted out through the fracture network almost instantly and without too much pressure loss. So these are the things we're going to allow to be varied. And we're going to create this in a very simple, almost a cookie cutter model to start with. Now, this doesn't have to be your approach, but if I've got 500 wells sitting in front of me in the same general play, and somebody says, can you apply reservoir simulation to all of these wells quickly, just to give me a rough starting point, without having to depend on minimum B values or some other technique that doesn't account for all of these variables changing at once, this is really not a bad approach to start with. So here's my base case model. This is the aerial view. This is a 4,000-foot lateral in a 640-acre section. Okay? And I've got an initial 40 fractures in this model. Remember, four perf clusters per stage times 10 stages. This is a blown-up view of it showing the logarithmically spaced gridding that the hydraulic fracture wizard places around each one of these planar fracs. And I am assuming planar fracs in this particular case. And in terms of a 3D view, it's a 5-layer model. I just chose to make it 5 layers. But for starters here, I'm going to assume porosity in matrix perm is roughly constant through this whole system. I don't have to make that assumption, but is it necessarily a bad assumption? Not necessarily bad to start with. So here's a little bit of information about the grid system. My grid blocks, delta X and delta Y, I'm setting it to be, if you remember my frac spacing, I assumed it was 50 feet. I'm setting that to be the same, 50 feet spacing. My vertical layers, I've got 5 layers, and I've got 150 feet, so they're each 30 feet thick. You know, if you want to put 100 layers in there, you can. It's going to slow the process down. You can certainly do it. So that gives me 105 grid blocks in the X and Y direction and 5 layers. So my parent grid block system has about 55,000 grid blocks in it. And when I put in the local grid refinement to represent a particular frac geometry, in this case 275-foot half length with 40 fracs, it adds about another 34,000 locally refined grid blocks to this model. So I've got roughly about 90,000 grid blocks. Okay? So we'll see how fast this runs in just a minute. First thing I want to do is, with my uncertain data, I want to do a sensitivity analysis. Before I waste time doing a lot of history matching and allow everything to vary necessarily, I want to see the sensitivity of matrix perm to my cumulative production of oil and water and gas and even my flowing bottom hole pressure. Same thing for the matrix porosity, the initial water saturation, and the natural fractures. I'm supplying it with 4 different compaction tables because I don't know which one is going to fit the best. So I'm going to give it 4 different ones. You'll see what those are in a second. My prop frac half length, again, I'm varying from 50 to 400 feet, so on and so forth. Now, notice that these are set up to be discrete values. And until the 2013 version of CMOST came out, That's all you could work with in CMOST. Everything had to be discrete values. Well, now, in the 2013 version, I can work with continuous values, give it a min, give it a max, and a probability density function. That's brand new, okay, in the 2013 release. So this is the table that we're using now that shows that I'm going to allow these parameters to be continuous parameters. So it'll search the space and try to find anything in between or on the endpoints. And in this case, we're actually using a uniform distribution, but you can use log normal or whatever you want for any of these parameters. But I'm still holding these parameters like the rock type tables and the distance between fracs as being discrete values. I'm just choosing to do that. I don't have to. So the emphasis here, CMOST 2013 now allows you to treat parameters as being continuous values, not just discrete values. And here's my rock compaction tables from the worst case scenario. This is the perm multiplier as a function of pressure. Remember, my initial pressure is around 8,100 psi. So the least destructive case says that if I drop down and create a flowing pressure of about 3,000 pounds, I'm going to reduce my permeability down to about 0.2 of the original propped frac perm. Okay? Common output from sensitivity analysis, tornado plots, to help me quickly visualize which of those parameters that I'm allowing to be varied have the most impact on whatever target variable I'm looking at. In this case, it's my cum oil. So it's saying here that matrix perm has the biggest impact even after just 7 months. Well, why is that? Because the permeability of the natural fracs and the prop fracs is pretty high. Pressure moves out quickly as soon as you put the well on production. Matrix perm is what's feeding it. The next most important thing is the prop frac spacing, getting into the surface area exposed to the matrix, and the prop frac half length, so on and so forth. Matrix porosity here, very little impact on matching the early 7-month data. So I want to look at this for each one of my target parameters. Cum oil, cum gas, cum water, and flowing bottom hole pressure are what I'm using in this case to make up the global history match error that I'm trying to minimize. Okay? And also up here at the top, and although we didn't put in the historical data, how these parameters vary from min to max creates 3 lines at the top of these sensitivity plots. The historical data normally is shown here, but we want to make sure that we bracket with everything set to the minimum values. That value should be less than the target, and for anything set to the max, everything set to the max, it should be greater. So we need to bracket the historical data. Otherwise, it's telling us we can't get a match with this data. So you won't waste your time trying to do history matching. Because sensitivity analysis takes a lot fewer runs than history matching. And in fact, in this case, using the new capability in CMOST 2013, when you do sensitivity analysis now, it tells you how many experiments to run. Before, you had to give it a number. Now it tells you, and in this case it used 42 full simulation runs to create the sensitivity plots that we're seeing here. When we did this presentation with the discrete value version of CMOST, we set it to do 100 runs. We didn't know. Okay? So it's a lot more efficient now just to do the sensitivity analysis. And this is the plot for cum water. As you might suspect, the cum water, remember it's frac water being produced back, is most sensitive to the initial water saturation in the prop fracs. Intuitive. But I didn't make this happen. This is what the process told me, so that's good. Cum gas, same thing. And flowing bottom hole pressure. So very easy to see which parameters are most sensitive. If you want to do this with 100 parameters at once, you can do it. It's going to be slower, but nothing keeps you from doing it. So now that we've got sensitivity analysis, I want to proceed to doing the history match. And no, you don't have to do sensitivity analysis if you don't want to. You know, it's 40-some runs that get occupied, but we'll see how long this process takes in just a minute. So it's not a bad idea to do the sensitivity analysis. So for the actual history matching, I have the same 8 parameters, and I'm giving them ranges. These are the continuous parameters. These are the discrete values for my rock compaction and my spacing. And basically, you as the user of this technology tell CMOST how many simultaneous runs you want to be able to make. Obviously, that's a function of how many licenses you have available. But you know, when you run IMEX, one IMEX license driven by CMOST, does everybody know the multiplier? 4 to 1. It'll let you run 4 simultaneous instances of IMEX with one IMEX license. Okay, so it's a pretty good value generator just to use CMOST to do that. Okay. So what are we looking at here? We're looking at the global objective function, which is designed by you, the user. In this case, it's a weighted combination of the oil match, the gas, the water rate, and the flowing bottom hole pressure. And you can see, and this is plotted versus run number. The base case model generated a global history match error of about 38%. And you can see these are all full simulation runs here. Every one of these blue plots. I know you can't quite see that, but trust me on this one. And as time goes on, you can see very quickly CMOST finds some combinations of data that drive that history match error down to less than 5%. And by the way, when we do this with the 2012 version of CMOST, it takes it a lot longer to get to that level, probably twice as many runs. For whatever reason, we keep making improvements. Okay? And you can see there's a lot of runs here that are down close to the minimum value. This red dot's the actual least history match error. I know it's kind of hard to see that. But by the way, while you're running this, if you're looking at this on your computer screen, even if these runs are running on the nodes of a cluster or the nodes of a virtual Amazon cloud system, which no reason you can't do that, okay? You might decide to stop the whole process after 100 runs, depending on how long it's taking and how many licenses you're occupying to do this. Okay? But obviously, we're trying to drive that down. So overall, we took about 350 runs. And you can see it's trying to search, make sure that it's not stuck in a local minimum somewhere. And so that's what we wind up with. So while this is going on, you're just monitoring this process. If you want, at some point here in the near future, we can even monitor this process on your iPad with CMOST Mobile. Maybe you've heard that before, but that actually can be set up. Assuming your IT people will allow you to access where this stuff is running. That's not a small assumption. Okay? So here is the list of the top 15 jobs in terms of ranking by history match error. I know you can't quite read the numbers, with the best case at the top. And so I'm going to go to this next slide. These are the actual parameter values that CMOST selected for the very best case, the one with the least history match error. Okay? So you can see we're at about 520 nanodarcies matrix perm, which is kind of in the ballpark for what people think about the Eagle Ford oil window. About 6.6% matrix porosity. Everybody would love that to be 10%, but when you crush cores and get a porosity, guess what you get? Total porosity, not effective porosity. Okay? And I got to talk about that type of subject for forever. Okay? And the natural frac initial water saturation, 26%. Prop frac half length, 247 feet, effectively, as far as the data is concerned. Okay? And the prop frac perm, 23 darcies, pretty high. Prop frac initial water saturation, 35%. It's actually kind of nice that that comes out higher than the initial water saturation in the natural fracs that are connected to those. I think that kind of makes sense. Prop frac spacing, it's not 100 feet. It's telling me that the data is suggesting that only half of your perf clusters have an effective fracture. Now, I think a lot of us know this from tracer analysis, things like that, but it is kind of interesting to see that the production data can kind of help tell us whether that's true or not. Okay? And we see that a lot when we apply this approach. We see a lot of cases where it's never greater than the number of perf clusters. It's always less than or equal to. So these are data points that could help drive you to going back and trying to figure out, what are we doing not so good on designing or placing these fracs? You know, because that's how it's behaving. That's what you're getting for your frac dollar, is less than what you paid for. So there's lots of room for improvement there. And then the compaction table that got selected was the least detrimental one, the one that gave us the least amount of loss. Okay? Everybody likes to see the results of history matching in terms of, well, how well did it match the data? These are all plots directly out of CMOST. These plots have actually improved in quality a little bit. Here's my cum oil and oil rate match. Now, I'm driving this model during the history phase with the oil rate. So I better get a match on that, assuming I have enough flow capacity in the model to even match the early rate. And we do, okay? Mainly because of the local grid refinement. Don't match the initial capacity by putting in a high matrix perm around the well. That's total nonsense. You can make it match, but then your assessment of time to pseudo-steady state or time to interfere between wells is completely wrong. Okay? You got to use the right design of the grid system, and don't mess with matrix perm. Don't stimulate the matrix perm. You're stimulating with the prop fracs and the natural fracs. Here's the gas rate match. Because this wasn't locked in, simulation results can go above and below, but you can see the blue data, that's the actual. And most of our best cases match in there. You can see how well the rate matches. It's a pretty good match. And this is our frac water production match. Even at early times, we're matching it quite well. Now you'll see here some of the optimum cases don't match every target equally. You're trying to optimize on multiple targets at the same time. So just because one match matches cum gas well doesn't mean it's going to match flowing bottom hole pressure equally well. And this is our bottom hole pressure match during this process. So now let's take the 15 best cases and let's extrapolate them out for 30 years at some fixed operating constraint like flowing bottom hole pressure. That's what I did in this case. And you can see that they give a range of values of cumulative oil production after 30 years. And those ranges in this case are represented here, a min, a max, an average, median, standard deviation. To me, these are easy to justify numbers compared to doing this from some other less sophisticated analysis technique. And as long as we can make this happen quickly, efficiently, I think it's a reasonable alternative to other types of analysis techniques that are out there. And this is our gas EUR. Same thing. By the way, this is about 5% recovery after 30 years. Okay? I'm being told to hurry up. Okay. All right, so here's the bottom line. How long does it take to do this? Okay. Come to training, get a little bit of training on CMG. I'm being generous here. It really doesn't take 8 hours to set up these base models. It takes minutes to set them up. Even if I have to import a full corner point grid from Petrel or RMS or GoCat or whatever you're using to create your base model with, if I want to extract a submodel from that to look at one well, I can do it very easily. You know, the beauty of these tight reservoirs is a lot of these initial analyses can be done assuming the well's in a world all by itself. Because it takes a long time, unless you connect up to a well by fracking, it takes them a long time to interfere just due to pressure transients moving out. So there's a lot of good stuff here. 42 CMOST runs. Those 6-7 month runs took 1.6 minutes to run each in IMEX. So we're looking at about an hour to do the sensitivity analysis as far as compute time. Now obviously this is a function of how many licenses you throw at it, the speed of your computers. This is all done on one blade or one desktop machine in this case. 350 CMOST runs, and I could have stopped them earlier, as you saw. Took about 1.5 minutes per run. So we're looking at about 8 hours to do the whole run. So a total, and then we took the 15 best runs and forecast them out for 30 years. That took about another hour to do. Going from 7 months to 30 years of production, went from 1.5 minutes to 3.5 minutes per run. Not so bad. So we're looking at about 10 hours of compute time. And in this particular case, we're making 4 simultaneous 8-way parallel IMEX runs for the history match and sensitivity analysis, and for the 15, 30-year forecast. We just did those one after the other using 16 cores per run. Okay? And that's the horsepower in terms of the processing. So pretty reasonable to look at doing something like this in a day or less. Okay? Now what if you have 500 wells? Well, you could consider renting yourself for a day at Amazon's cloud for 500 different virtual versions of that hardware. They have it now. You can create a virtual hardware, 16 cores, 32 cores, 60 gigabyte of RAM for a certain, it's like if you do it on spot pricing, you can get it for about $1.60 a day. No, sorry, $1.60 an hour per core. So, you know, this is, everybody says, well, I can't afford to do this on all my wells. I don't think you can afford not to do it on all your wells. And I think it's possible to do that now. So let's go on, a few more minutes here. What about using this information to optimize the number of stages, the size, etc., and then the well density? So choose the simulator, build the base model. We're going to do sensitivity analysis again. We're going to do optimization. In this case, we're going to optimize on NPV. You can do it on any economic yardstick you want. And we're going to optimize well spacing. Again, you build a base model, decide which parameters you want CMOST to vary, and let CMOST do the rest of the work. So we're going to start with our same Eagle Ford well, only this time we're going to lock it in. I don't have to, but I'm going to the values from the best case history match from that previous work. Again, you don't have to. You can give it a range, whatever you want to do. And I'm locking it into the same compaction table. So we're going to add some economic information here. Pretty typical data. Oil price, gas price. This is probably a little high for the Eagle Ford right now. People are getting very, very efficient with the rigs on tractors. And in the previous version of this study, we even had that down to $3 million per well drilling cost. The key thing is the frac cost. And in the previous version of this talk, we just had a fixed frac cost per stage. It wasn't a function of frac half length or perm. In other words, volume, horsepower, and amount of proppant pumped. Well, now we've got a function in here that's going to allow those things to vary, the cost of the stage to vary with frac half length and perm. This is not easy information to get hold of. We just came up with a function to demonstrate that you could incorporate it in the process, but there's no reason why you couldn't use your field experience on this or sit down and talk with your service company that's pumping your jobs to try to come up with a better tuned model for this fracture cost model, because it's pretty important. And we're going to do a forecast 30 days. So here's how we're incorporated. This is a screenshot out of CMOST. I know you can't read this. All I'm saying is you're inputting the cost function for the cost of the frac stage. In this case, it's varying with frac half length. You can see the cost from $200,000 to $600,000 per stage. That may be totally bogus, but this is what we used in our example. And the cost per stage based on the amount of frac permeability created, which is a direct function of the amount of proppant pumped. 10 cents a pound, right? And here's the variables that we're going to allow to be changed to do this optimization of a single well and then multiple well scenario. We're going to let the well spacing vary from 71 acres to 640 acres. That translates into 9 wells in 640 acres or 1 well in 640 acres. I'm going to keep the lateral length the same, and I'm going to let these other 3 parameters vary. Pretty straightforward. Here's I'm just using discrete values in this example. I don't have to. I can use continuous values. I'm allowing the prop frac length, the frac perm, and the frac half length to vary. So there's 252 combinations of data here. That's actually small enough with these runtime speeds to run every case, brute force. But again, the optimizer does it a lot quicker than that. So here's my NPV for a single well versus run number. We call it experiment ID. There's the best case scenario, about 1.25 million is that 1.2, 12 million, sorry, of NPV, again, based on the frac cost model that we've got. And again, just like in the case of history matching, you're just monitoring this process as CMOST chunks through all the example data sets it wants to do. In this case, the optimum parameters suggested 100 feet spacing between perf clusters, 5 millidarcies of prop frac perm, and fracture half length of 300 feet. Now, when we see data that gets selected that's on the ends of the range, first thing you want to do is think, maybe I should investigate other values near that endpoint. Maybe that's not the optimum. In the old version of CMOST, you'd have to rerun the whole experiment. The new version of CMOST, you give it another value. In this case, I'm going to add a value in between 200 and 100. Could have been 50 feet, but I doubt if it's 50 feet. And when we do that, with the new version of CMOST, this was the original case without the 150-foot spacing. This is the new case. All it does is adds 15 more runs to the process. So the new CMOST is very powerful. It can use previous data to expand a task, if you like, or to go from sensitivity analysis to history matching. Very, very big gain in efficiency of this process. So again, if you're not using this feature, I want you to be aware of it, at least. Okay? So no need to restart the whole process like prior to 2013. And it just turned out that 150 feet was closer to the optimum spacing than it was previously when it showed 100 feet. So that's kind of interesting. So here's my optimum design for a single well. I'm just going to apply it now to 1, 3, 5, 7, and 9 wells, keeping the frac half length and everything constant. Okay? So what this is showing me is my cum production continues to increase. Even with 9 wells, it's increasing. But what about my economic yardstick? In this case, the NPV maxes out at the 7 wells, and because of the cost of frac treatments and holding the frac design constant, I actually see a decline if I try to go to 9 wells in the section. Okay? Now, this is applying the same frac design to each well in these sections. I also wanted to go back and redo this and let CMOST decide what the optimum frac half length is as I add these wells. And as it turns out, for the 9 well case, okay, where before we were using a 300-foot half length, and etc. If I allow the frac half length for all 9 wells to be varied as part of the optimization process, it actually winds up giving me a higher NPV for the 9 well case, and it actually reduces the frac half length. Well, it makes sense. The more wells you throw in there, the shorter the fracs need to be, right? You don't want them overlapping on purpose. You'd like them touching, ideally. So it affects the economics there. So again, this is all doable with the current technology. That's a big thing I want to emphasize here. This isn't, well, where we want to go with our workflow. This is what we have right now that you can use. Okay? And a lot of people like to see things like this. This is a plot. These are plots of matrix pressure after 30 years of production with the 9 well case and the 7 well case. And yes, they do interfere, but not enough to negatively affect the economics. Okay? You can see here, though, that outside the range of this, we still have some matrix perm that's almost close to original pressure. It's tight. And how long did it take to do all this? 85 CMOST optimization runs took an hour and a half, and 4 30-year forecasts took a half an hour, so 2 hours. Okay. Can you afford not to be doing this? I don't know. So, a little more on the credibility building side of this thing. You don't have to take my word for all of this. I just did a quick search on OnePetro looking for how many SPE papers mention the word CMG and unconventional gas in them. Right now it's about 79. Now you know how OnePetro works. Sometimes stuff that's not related sneaks in there, but that's what you'll see right now. Most of them are papers that feature the use of CMG software for this type of modeling. And for the unconventional oil, it's 43 hits. Here's a couple of recent papers that have just been published over the past year or so. This is a paper presented by a couple of folks at Texas A&M, including Bob Wattenbarger, who's a pretty well-known professor there, and Stan Maketa is Chief Reservoir Engineer at Southwestern Energy, a recent convert over to CMG for doing this type of work. Estimation of effective frac volume flowback using IMEX to model that process. They make a lot of important comments in here about the importance of modeling water flow back with a numerical simulator as opposed to using standard diagnostic things. This is an interesting paper. I talked about geomechanics module here recently. Our friends at Chevron, who are licensed users of our software for this type of work, this gentleman, Padmacher, used GEM with a couple geomechanics module. Because it has this Barton-Bander feature for allowing natural fracs to vary in their permeability with stress, he actually uses it to design and history match defits with the added advantage over standard techniques that you can model what happens after closure. Because we're modeling leak off and all the things properly. So it's a pretty interesting paper. This is another one. This is from Shell folks talking about the use of our software for their Marcellus play, GEM and CMOST. Probably know Shell's one of CMG's biggest customers worldwide, especially in North America. And this is an actual paper at ExxonMobil. They would never admit to using our software in the paper, but Yitian Xiao has been using GEM for doing CO2 sequestration, and now some of the folks using it for gas shale stuff. This is a Fayetteville paper, again using GEM. Doesn't mention it, but the plot's in the paper, and we know who did the work, so it's another example. And of course, Barry Rubin, I wouldn't be standing here today if Barry hadn't done his work back in the 2008-2009 time frame. Got that work implemented in terms of the hydraulic fracture wizard in Builder, and thanks to the visualization team guys for getting that done. They give me the tools to be able to do this stuff, and it's pretty exciting. And just to give you a little idea of things coming, this is using the current GEM plus geomechanics feature to model fracture growth in a situation here where the principal horizontal stresses are different enough to produce planar type geometry. On the right and on the left, we're producing complex geometry where the principal horizontal stresses are roughly equal. So we can actually do some of this stuff now. It's kind of cool. All we need to add is prop transport and gelled fluids, and we're going to have ourselves a frac design simulator that's full 3D, geomechanics controlled. In other words, the effect of stresses on stage 1 will show on stage 2, etc. Stress shadowing, that type of stuff. So this is a direction that anybody who's modeling production from frac wells needs to be looking at. Because to really do a better job of setting up the base models, we really need to have a better idea of what the geometries are that we're creating. And from that forum that I was at, and I'm going to finish up here in just a second, you know, the design, the modeling of hydraulic fracturing is the weak link in this whole process. Because the existing commercial products do a great job if you're assuming you're creating a single planar frac. Okay? But they're not so good about looking at the big picture and multiple fracs in the same well. Having said that, we are actively working with the folks at Meyer & Associates, you know, MFRAC and M-Shale, Bob Berry's group, the Gopher product, and Mike Smith's group, StimPlan. You all use different packages for this, so we want to be able to import their conductivity maps into the hydraulic frac wizard so that we can put in a non-uniform distribution of perm, etc., in these planar and complex fractures. So that's part of where we're going, along with the idea of maybe doing some of this hydraulic fracture simulation ourselves. Okay? And one last thing. Do we have enough physics in these models to model the process? We all heard this topic of nanopore scale physics, bubble point depression, dew point depression, Knudsen diffusion. If you look, and I have, if you look at all the papers that have been published on this, they all talk about these effects becoming significant at pore throat diameters at 50 nanometers or less. And what does that mean in terms of what we're really producing from? Well, if you treat 50 nanometers and you're looking at a straight capillary tube model, that's a pretty high perm. It's like 15 microdarcies. But if you look at it in terms of a tortuous rock flow model, and in this case we're using the equation of Katz and Thompson, published in 1986, that relates pore throat diameter and porosity to matrix perm. And this was reported on and validated in Nelson's API geologic note in 2008. That translates into 28 nanodarcies of actual rock permeability. And you know, there aren't many commercial liquid plays that are operating at this level of matrix perm. So I'm just not so sure about how important including those physics is in the process. I love what the universities are doing to try to test all of these things, but I don't think anybody's done the checkpoint, is this really necessary? So we're paying attention to it. We'll put this stuff in if everybody winds up thinking it's really important, but I'm kind of guessing maybe it's not. Who's using this? I'm not going to leave this slide up very long. A lot of your companies are up here. Almost all of these but one is in North America right now, US and Canada. So there's quite a big list. And there's the final message. I think physics-based EUR and well optimization using reservoir simulation, it's doable now in hours using the workflows enabled by our current release of the software. And with that, I'm going to close, and I guess we're going to open up for questions. So we have a microphone in the center of the room. We're going to make you walk to the mic because everybody wants to hear your questions, if you have any. Willing to entertain anything. And for the, how do we address the frac azimuth? By orienting the grid right now is the best way to answer that question. If we're using our geomechanics stuff to help decide where these fracs are going to grow, we can actually orient the geogrid different than the flow grid. So that's one way we can kind of address it. But we're taking a look at some alternative technologies there, like adding unstructured grids as well to try to address that issue. But the real question is, I mean, look at a DFN that you see coming out of this. The stuff's going everywhere, right? Do you really need to model every one of those in every one of those directions? I kind of doubt it, and it's not going to be really practical to do it. I think if you represent it as a series of cubes in terms of the natural fracture network, that's probably pretty good. I also think that representing the variable conductivity, and I should have said that in these examples here, we varied the permeability of the prop fracs from the mouth of the frac to the tip in a linear fashion, because that's one of the features that's in the hydraulic frac wizard now. But to me, it's about the permeability right near the well, because that's where all the fluids has to go through. So I'm kind of betting that we're not going to see that much importance of tapering that permeability in the prop fracs. Questions? We have a question over here.
Do I have to use the mic?
Please, because there's people listening outside this room.
All right. For most of us in Alberta that are dealing with Cardium tight oil wells, where we're not so lucky, where in very few cases the well might be flowing for 1 or 2 months, and then it's on pump.
Yep.
So what's your advice in using your model to kind of make adjustment for that type of wells?
Sure. Great question. I think everybody heard that. When you're going to do the history match part of this thing, you obviously are going to use a flowing well situation while the well's flowing, okay? Because nothing prevents you from adding a tubing intake curve into this model and driving it or matching it with, say, flowing wellhead pressure if you don't have a bottom hole pressure. When you get to the point in time where you're in the data where you switched over to a pump, then your operating constraints are changed. If you're pumping at a certain rate, hopefully you have some idea what your fluid level is. That's the flowing bottom hole pressure that you're pumping against. So you might drive the model with that bottom hole flowing pressure while you're in the pumping phase.
So is there a way you adjust the fluid level because you don't have any bottom hole flowing pressure, obviously?
Well, for years, people have used echo meters if they don't have any better way to do this. Now, there's some disadvantages to that, foamy oil columns and things like that, but it's better than guessing. But worst case scenario is you just assume that, hey, these wells are being pumped off to a certain fluid level, and let's put that in as the starting assumption, and then use that as a variable. Hey, it's a range of values. But you do have to adjust the operating constraints of the well to fit the lift system or lifting technique that you're currently using.
Actually, that's probably not a bad advice because in most cases, wells that have been involved, they're pretty well all pumped off.
Yep. Yeah, if they're pumped off, it's actually pretty easy. Think of the IPR curve at a bottom hole flowing pressure that's fixed, right? These reservoir simulators are generating one fancy transient IPR curve. That's what they're doing, taking into account all the physics. That's really what's happening here. But you still have to model the well right.
The next question is, what kind of standard deviation would you be looking at if, in most cases, in real life, you're not looking at a single linear fracture? In other words, if we don't use the next phase model that you have, where you talk about adopting the mechanic, what do you call that? That's coming up next.
Oh, the mechanistic hydraulic fracture simulation?
Right.
Well, I still think before we even get there, if you have an approach like this that says, these are the parameters that currently describe how the system is behaving, to me, that's a good starting point. Okay? I mean, obviously, the more data we have, the more refined we might be able to get in terms of what's coming out of this particular stage or cluster. Tracer data, incorporating that into the history matching process. These are all things that can sort of increase the level of detail that we can drill down to. But again, I'm trying to get people thinking that every one of these is not a science project, okay, to begin with. If I'm going to do data analytics on a whole set of wells in a field, I already know that it's well location dependent. I want to know the perm in each one of these that I can correlate to. That's much more important than just correlating to a bunch of things that we already know. Yep.
I have another question about the optimization.
Okay, hold on one second. I'm used to this from the forum. We make people get the mic.
One more question about the optimization process.
Yeah.
Some of these hydraulic fracs, they grow out of zone. And how do we address that in the optimization?
Well, I think by history matching to see what your effective frac half lengths are, that's going to tell you a lot about what your frac height must have been, right? If you come up, because you're obviously going to come up with a much shorter frac half length. In this example, if I had the frac design data as a guide that says, well, these frac half lengths should have been 750 feet, and the effective lengths are coming up a lot smaller, what is that telling you? Maybe I have a frac height problem. I need to go out and measure something during the job or after the job, temperature surveys. I need more data to help resolve the answer to that. So that's all I'm saying is that right now we know we've got production data. Maybe we've got a flowing wellhead pressure. Please measure it. Let's get some data that can help start directing us toward answering those kind of questions. Because without it, you really don't know where you are.
I have a question from Houston. Please explain how you modeled the dual perm system. How is it different from a single perm system with higher effective matrix perm? You indicated that you are using a dual perm model in this project, but I didn't follow the differences.
Yeah, okay. So it was kind of what I was referring to about adjusting the matrix perm to get enough flow capacity to be able to produce. That's not what's happening in these wells. The matrix perms are relatively low, and when we pump a frac job, we're putting a prop frac in there, and we might be opening up some existing fracture planes, creating these little conduits of high permeability distributed amongst the matrix. Okay. To model correctly transient flow from the matrix feeding into these systems, you cannot go in there and just say this is going to be a single porosity of a higher effective, people call it the SRV effective perm. Oh, I hate that term. That's homogenizing the whole thing. You will never get time to interference between frac planes or time to interference between wells correctly if that's the way you model to meet the flow capacity. Okay, so I hope that answers that question, but that's why we use dual perm to represent the stimulated and the non-stimulated matrix either away from or close to these prop fracs.
Another question this is from Dallas. You mentioned that the GOR in the Eagleford stays the same. Can you explain the reason again?
Yes, because even though the flowing bottom hole pressure drops below the bubble point, for a long period of time, the pressure in the matrix doesn't drop below the bubble point. And the fact that these are high conductivity paths inside the prop fracs, the concept of critical gas saturation or relative permeability being straight line behavior as opposed to being curves, you just don't see the interference between fluid phases. It continues to produce at equal rates. So you just don't see the GOR change.
And then from the UK, we have, how do you cope with geological heterogeneities? Example, variations in natural fracturing in the 0.5 times 1.5 kilometer sector are you simulating? Have you tried CMG on models coming from Petrel?
Absolutely. Any one of the major 3D geologic modeling packages, any properties that they've modeled inside those can all be directly imported into Builder in the form of a rescue file. So that's the starting point of your grid. So the more information you have about how porosities, permeabilities, and fracture spacing vary from one location to the next, whether it's a regional scale model or a smaller scale model, that can all be incorporated into the starting point of this process. Now, those models are going to run slower than these little cookie cutter models, no question. And if I want to allow matrix perm in a distributed environment like that to change, I'm going to use it as a porosity perm modifier and give the modifier a range of values that lets me say, well, maybe the relative values between grid blocks is correct, but the absolute numbers aren't correct, so I want to include that in the history matching process. Totally doable.
And then there's someone from Calgary who's online. When we do the well optimization, we change the cross length, fracture width, and we calculate NPV. What is the relationship between fracture permeability and fracture width or fracture length?
Well, they all should be tied together. There's no question about that. Same thing for natural fracture properties. One of the things we do in these simulators sometimes is give ourselves too many degrees of freedom. If you're going to input frac spacing and frac width, that translates to a fixed porosity and a permeability. It should not allow you to just put anything you want in there. And to answer the question about the prop frac properties, from the production data, we know that the prop frac effective perm and length has a big effect on production. How you translate that into the amount of fluids we pump and the amount of proppant we pump, well, that's a function of how well you can model the injection process. And we can do some of that now, but that still needs to be improved.
We'll just take one final question, then we'll wrap it up, and we can stay afterwards to discuss further. So it looks like you wanted to ask a question?
All right. Yeah, like you mean?
Sure.
Actually, I had two questions. The first question comes back to the more robust approach for simulating the hydraulic fracturing. Can we, do we have something like FlexWell to more focus on the wellbore simulation? Adding to
that's another aspect of hydraulic fracture simulation that I think needs to get looked at. So just like we've gotten more detailed about modeling the startup circulation phase of SAGD with more sophisticated transient segregated flow wellbore models, I think when we look at developing enhanced fracture design simulators, they really need to look at the effects of flow across perfs and all that sort of thing. Absolutely. So yeah, I think there's a place in the future for enhanced wellbore modeling as part of the hydraulic fracture simulation process.
All right. Can I ask another question? For CMOST optimization, for MPV actually optimization, is there, we need to write Java codes for CMOST, yes?
No. There's a built-in NPV function now.
Oh, all right, I didn't know.
The only place I used Java code in this example was on the cost function. But you don't have to do that with Java code. CMOST will talk to your spreadsheet. If you have a cost model in a macro in Excel, you can point CMOST to that to bring back that parameter. Okay,
Thank
so
you.
you don't have, and we are looking at taking that to Python anyway for those of you that are into the programming side. But our support people in Calgary, Houston, all over the world are pretty good at JScripting. So if you have things that you want to do not hesitate to call our support groups in these locations. We've done a lot of that kind of work. Okay?
All right, please join me in thanking Jim for the presentation this morning. We'll stick around.